Hello everyone, I'm pleased here to introduce our research work DCONST, Detection of Multiple Mixed Attack Malicious Nodes Using Consensus-Based Trust in IoT Networks to you. With the development of IoT network is widely used in the industry monitoring, robot network, smart home, and something case like this. And in these cases, it suffers from serious insider attacks. For example, like this wireless sensor network, when hackers hack the end devices, like the sensors or some end devices, then it can control these devices to make some inside attacks. For example, like the tamper attacks. That means these malicious nodes can tamper the data it received so that it can make the damage to the function of the network. And for the robot network, which is a cluster-based network, also suffer from the same attacks too. And then we face some challenges. Existing research works focus on a single attack scenario, so that we just want to focus on a multiple mixed attack scenario, which means our malicious nodes will have more than one attack abilities. For example, a malicious node can launch the tamper attack, drop attack, and replay attack together. And most existing work just detect anomaly phenomenon. For example, for those anomaly detection systems, they just focus on discovering the anomaly, but they will not locate malicious end devices. So we want to locate malicious node devices as well as identify their concrete behaviors besides detecting attacks. And most of methods make the judgment from only one node. That means if the malicious node makes some evil judgment about the benign nodes, then it will have a false alarm. Then we want to judge malicious nodes with multiple opinions from the whole network. For the IoT network, most of end devices have the properties of the resource constraints features, so that we want to achieve the detection with a lightweight weight. Besides, we want to propose a general framework instead of just achieve the narrow applied detection. For example, when we have to cope with some new attacks in the future, we just need to make some small changes so that it can work with the old framework. DCONST achieve and cope with above goals and by following methods. The first one is it can deal with multiple mixed attack and identify concrete malicious behaviors by designing multiple dimension trust and corresponding detection mechanisms. And for locating the malicious end devices, it can share particular information which we call cognition to achieve this. About judging malicious nodes with multiple opinions, DCONST use consensus to judge malicious nodes. To achieve the lightweight detection, DCONST adopt some lightweight signatures and verification mechanisms. In addition, DCONST is a general framework, and it's achieved by general cognition sharing, general trust evaluation, and designing specific evidences. And when we have to cope with some new attacks, we just need to design corresponding evidences and add them to the framework as a component so that it can work with the old framework. Now this is the workflow of DCONST. it has two processes. The first one is the trust evaluation process. And with the daily running of IoT networks, each node will have the cognition about other nodes in the network, so that from the whole network we can obtain a cognition matrix like this form. For example, the COG12 means the cognition of node 1 about node 2. And then from this cognition matrix, we can make a final calculation to calculate the trust of each node, just like this. And in the malicious node detection process, we input the trust of each node to the k-means clustering module. Then we can obtain the tamper malicious set, including those nodes who launch tamper attacks, and the job malicious set, which launches the job attacks, and the replay malicious set include those nodes who launch the replay attacks, and the benign set includes all the nodes who are benign. This is the node model of DCONST. ID T means the multi-dimensional trust of each node. And PR and PU means the public-private key pair used for encryption, decryption, and signing. COGL means the list of cognitions, including all cognitions of the nodes about others. And the PTA, PDA, and PRA are the probability about a node launching a tamper attack, a job attack, and a replay attack respectively. And this is the message model of the IoT network. The M is the message. D is the original data that need to be transferred. The PUR is the public key of the receiver and is used to encrypt the data so that it can defend the inside attack. The SID is the signature about the original data. COGXIYI is the cognition of node XI about node YI. The XIYI is the signature of the COGXIYI and is generated by the node XI. The K is the symmetric key, and K is used to encrypt the whole message. This structure is used for cognition spreading and recording the history of packet. For example, when we see this message, we can obtain the message transferred by the path x1 and x2 to xn. This is the trust model of DCONST, corresponding to 3 attacks, that's tamper attack, job attack, and replay attack. We design 3-dimensional trust. The H means the honesty. It's the dimension that demonstrates whether a node tampers the received data or not. The V means the volume, the dimension that illustrates whether a node drops the received data or not. S is the stray. It's the dimension that concludes whether a node replaces the received data or not. And this is the cognition. Cognition includes S sub, the subject of the cognition, and the object of the cognition. And its name means whether the subject is the neighbors of the object. For example, if the node X and node Y are neighbors, and the honesty, the volume, and the stray of node Y set as 100, 150 respectively, we will have a cognition X, Y, 100, 151 of node X. This means the cognition of node X about Y. Then after designing the cognition, how to build the cognition? We build the cognition by creating the trust gap between benign nodes and malicious nodes through punishing the malicious nodes and avoiding benign nodes. That's, we hope the trust of malicious nodes could be lower as possible, and the benign nodes should have a higher trust. This is the graph about the attack, and in the normal cases, we can see the packet starts from the node S and it passes node N1, N2, N3 until it arrives at D. And then the node D will return the ACK to the node S to notify that it has received the packet. But if the packet suffers from a tamper attack, for example, the N2 launch a tamper attack, then the packet will be modified as packet point. Then when D receives the packet, it will know that the packet is tampered due to the verification about its signature and its content. Then it will return the ACK to the node S. When the packet suffers from the job attack, then when the packet passes N3, the packet is dropped, so NT and D will not receive the packet. Besides, the D will not also send the ACK to the N0, so that the N0, N1, N2 will know that their packet has been lost. About the replay attack, when the packet passes the N3 will replay the packet so that there are multiple packets arrive at the D, and the D will send redundant ACKs about a packet to the N0, so that the N0, N1, N2 will know there is a replay attack. About the punishment of tamper attack, we have two cases. The first one is destination punishment, because this punishment is generated by the destination node of the path, that's the D. When the N2 tamper data, the D will punish the NT, N3, N2, and N1. And when the N2 tamper the cognition, the D will punish the NT, N3, N2, but not N1, because the cognition is the cognition N1, N3 is the cognition of N1 about N3, and the N1 will not tamper its own cognition. And about the middle punishment, that's the punishment generated by relay nodes. The N2 tamper the cognition N1, N3, then the N3 will check this cognition by its signature, and then the N3 will punish the N2, and the NT will punish N3, and NT will punish N2. About the punishment of job attack, when the N3 drop packet, then the N0, N1, and N2 will not receive the ACK from the node D, so that the N0 will punish N1, the N1 will punish N2, and the N2 will punish N3. Essentially, this punishment can form the potential punishment chain of these nodes, and we know one of these nodes is the malicious node. About the replay attack, it's just like the punishment about the job attack. When the N3 replay packet and the N0, N1, and N2 will receive redundant ACKs from the node D, so that the N0 will punish N1, and N1 will punish N2, and N2 will punish N3. Now we have to evaluate the punishment. The punishment, in fact, is the update about the cognition of the punishment provider. The UCOG means the updated cognition of the punishment provider, and the OCOG is the old cognition of the punishment provider. And the theta is the parameter that determines the reduction of the H. So from this equation, we can see when we make the punishment to a node, then we will minus a parameter here. Then we can reduce its trust of the cognition. And we use the log function here because the log function has a trend that when x coordinate is small, the variation of y coordinate is steep. But when the x coordinate is big, the variation of y coordinate is gentle. That means if we have to punish a node with a high trust, we hope the punishment should be lighter. But if we punish those nodes with lower trust, we hope the punishment should be serious. Because those nodes with lower trust are more suspicious. And V and S all follow the same rules. The award is the reverse process of punishment, and we use a counter to record the number of normal transmission. That's because for the punishment, when we detect a successful attack, then we just execute the punishment. But sometimes the malicious attacks will not always execute malicious attacks, so that we cannot just award the node of the pass just because it transferred a packet successfully. So we use a counter. For example, when in this pass the node successfully transferred 10 packets or more, we just give 1 award. And this is about the cognition aggregation and cognition sharing. Just like this, the data starts from the node S, and when it passes N1, the N1 will add 3 cognition following the data, and then it transfers this packet to the next hop. The N2 will add 3 extra cognition of its own, and then transfer this packet to the next hop, so that it can be shown in this figure. And we have 2 problems. How to update cognitions. That means when we receive a cognition from others, for example, the node N2 received the cognition from N1, how to update the cognition of it. And how to select cognitions to share. Because each node has the cognitions about others in the networks, so if we just select all cognitions of it to share, it will be inefficient. So that we have these 2 problems to solve. And the first one is about the cognition aggregation. That's about how to update the cognition. We will update the cognition according to 2 dimensions. The first one is the reliability. It can be formalized by this equation. And the N is the node. The C is the cognition about the node N, and H max, V max, X max are the maximum of H, V, and X. The second dimension is the fluctuation. That could be shown like this. And the NCOG is the new cognition, and the OCOG means the old cognition. In fact, it's the absolute value of the distance between the new COG and old COG. And we use these two dimensions means we think if the cognition is from a node with higher reliability and smaller fluctuation, we think it's more convincing. After designing the fluctuation and the reliability, we can formalize the credibility of a cognition by this equation. If the uncog's object is a neighbor of uncog's subject, and otherwise we set this parameter to be the rho I. In fact, the rho D should be bigger than the rho I because we think the cognition from a neighbor is more accurate. Then, with the help of the credibility of the cognition, we can regard it as the weight, and by this weight, we can mix the new cognition and the old cognition together. And we also use the log function too, so that we can update the cognition. And the update about the V and S just follow the same rules. Now we talk about the cognition sharing. We call this process the cognition extractions. We build three pre-queues. That's negative queue, reduction queue, and improvement queue. Negative queue means the cognition having the smallest sum of honesty, volume, and strength. And the reduction queue includes those cognitions that reduce the most and is updated recently. Improvement queue includes the cognition that improved the most and is updated recently. When we have to share cognitions, we will select three cognitions from these three queues individually. Then, when we have to detect malicious nodes in the base station, we will collect the cognition list of IoT nodes to the base station so that we can form this cognition matrix, such like this. And just like we mentioned before, cognition XY means the cognition of node X about node Y. And we have to know that cognition XX should be XX000 because we think the cognition from a node about itself is not valid because it could be a malicious node. Then we use the reputation as the weight when we calculate all the trust of the nodes. Then the reputation could be formalized by this form. Then we can see the REIX could be the WIX is divided by the sum of WKX. The WKX means the W when the node K to make the judgment about node X. And if K is equal to X, it could be 0 because just like we mentioned before, if a node have to judge itself, it should be invalid. Then the distance COGKX and AVERX means the cognition from the K about the X. It has a distance between the neighbors of X to judge the X. If the distance between this part and this one is larger, that means this cognition is more suspicious because usually the cognition from the neighbors of X should be more accurate. So that we formalize this like this. And then we can just calculate the reputation when the node I to judge node X. so that after we obtain the reputation, we regard it as the weight and we mix all cognition together so that we can form the final trust value of each node. Then when we have to detect malicious nodes, we input the trust value of each node to the k-means clustering module, and we can obtain 3 groups. That's temper benign groups, temper uncertain group, and temper malicious group. Only those nodes appeared in the temper malicious group will be determined as the final temper malicious. And we cluster all nodes to 3 groups instead of 2 groups. That's because to reduce the false alarm rate. And the detection of the drop attack malicious nodes and replay attack malicious nodes just follow the same rules. Now I introduce our simulation. We set a 100 multiply 100 square meters rectangle area, and each node's communication range is around 10 meter to 15 meter. Each experiment is executed in 10 runs with 10 different networks. For example, just like this case, this is the topology of the IoT network, and we set this node to be temper malicious node, and set this node to be replay malicious node, and set this node to be drop malicious node. Then we set the number of nodes as 7, 12, 17, 22, and 27. And we find that for other 2 compare methods, HD and PDE, they are easy to detect malicious nodes in small-scale network, but they are hard to detect malicious nodes in a large-scale network. Besides, we also set the probability of multiple mixed attack to be 0.1, 0.3, 0.5, 0.7, and 0.9. And we find that high attack probability is beneficial for DCONST, and it's hard for HD and PDE to handle over high attack probability, especially in the case of 0.9. In addition, with the percentage of malicious nodes under multiple mixed attack to be 0.1 to 0.5, we find that more malicious nodes improve the false alarm rate, but DCONST outperforms other schemes. And with the rate of valid passes to be 0.2, 0.4, 0.6, 0.8, and 1, we find that the network diversity does not have a significant impact on the accuracy of DCONST. So it can prove the stability of DCONST. Now we have the conclusion. DCONST can provide a better detection rate by around 10% to 40% as compared with 2 detection schemes. But we also have some problems to solve in our future work. The first one is how to defend the 50% attack. In our work, we assume that the attacker will not control over 50% malicious nodes, because if the attackers control more than 50%, the consensus of the whole network will be evil. Then it could cause a lot of false alarms. And besides, we also have to consider how to optimize the parameters of DCONST to deal with different network settings to improve accuracy and stability. For example, just like the theta parameter of DCONST will influence the performance of it. And finally, we have to deploy the DCONST to real IoT environment to test the performance. And we consider two deployment mechanisms. The first one is embed deployment. And we will inject codes to the programmable firmware of IoT devices. And the second one is transparent deployment. We will deploy some Raspberry Pis as traffic interceptors to process relevant data so that we can check the performance of DCONST without disturbing the function of IoT end devices. And that's all. Thank you.